Our topic this week is inference in probabilistic graphical models. That is, we're aiming to answer the question, given a probabilistic graphical model, either a Bayesian network or a Markov random field, we want to be able to do probabilistic inference. That is, output the probability of certain events according to that model. Specifically, this week we're going to focus on exact inference. That is, giving you an answer for that question exactly. Next week we're going to focus on approximate inference. As we're going to talk about today, in general, inference in probabilistic graphical models is computationally hard. We're going to look at a couple of cases where it's tractable, but there are going to be a lot of cases where it is not. So for those, we're going to need to resort to approximate inference. But this week, we're going to talk about methods for exact inference. So this is, we're going to switch this week to kind of more of an algorithmic focus. I would say so far we've had more of a mathematical focus, that is aiming to derive expressions for various updates, and only in a couple cases, like in the case of optimization, we focused a lot on the actual algorithms. These 2 weeks are going to be very algorithmic. That is, we're going to be looking at how to do these computations computationally efficiently. Okay, let's say more specifically what we mean by probabilistic inference. That is, we have some big Bayesian network or Markov random field with some perhaps complex structure. And in general, we're going to divide our variables into 3 sets. We have our query variable. That is the variable that we want to know the distribution over. Let's say, in this case, that variable is b. We have a condition or an evidence set of variables. Let's say that's d equals 1, e equals 0, just making up values. And we have our hidden or variables we don't care about, which is everything else. In that case, that's a and c. So that is, we're trying to answer the question, what is probability of b given d equals 1, e equals 0. So notice that if I want to write down this expression of probability, I put b in front of the condition because that's our query. I'm putting d equals 1 and e equals 0 in our evidence. And then the hidden variables, the don't care variables, they don't appear anywhere in this expression. By the way, we could have said we want the probability of b equals to a particular value, let's say 1. What we're going to do in general for these algorithms is we're going to give you the whole distribution over b as output. By the way, we're going to focus here only on discrete inference. That is inference over discrete random variables. All of the algorithms we're going to talk about here extend to continuous random variables, but things get more complicated because we need to represent the distributions over those variables. We can't represent them explicitly because that would require writing down an infinite number of probability density values. So we have to represent them with some sufficient statistics, and that becomes complicated. So we're going to focus just on discrete random variables here. Also, we're going to focus on cases where we have a single query variable. We could imagine queries also of the form like B equals 1 and C equals 1, but what we might want to know the case of that event, both of them happening together. There exist methods for those, for that question, but they get a little more complicated. So here we're going to focus just on the one query variable case. So mathematically, this is easy, right? We've done this 100 times before. If we want to know this conditional probability, we just need to plug it into Bayes' rule. This equals probability of B, D, E. I'm not going to bother writing the actual values just for simplicity, divided by probability of D. E. So that's easy, right? And then notice that we're given a Bayesian network or a Markov random field. That probabilistic graphical model doesn't actually specify either of these distributions. So in order to actually plug it in to our probabilistic model, we need to marginalize over the variables that aren't present. That is, we need to expand this into the following. Our Bayesian network or Markov random field gives us this full, complete probability expression. So we have to marginalize over the hidden variables, sum over all the possible values of A and C of probability of A, B, C, D, and E. Notice that now we have values for each of them. A and C we assigned in the sum, D and E we assigned in our evidence, and B we're gonna we could imagine assigning it here as our query, what's the probability of B equals 1, or we could just go through them one by one and do this calculation. If what we want is a distribution over, let's say, the 5 values of B, we could just do this calculation 5 times for the 5 possible values of B. And then same thing goes in the bottom here, but notice that we have to sum over B as well, because that's part of the query. Okay, so like I said, mathematically it's simple. Why is it difficult computationally? So for a couple of reasons. Number one is because of hidden or don't care variables. So notice here that I have to sum over all the possible values of A and C. So if there are variables in my network that I don't care about, counterintuitively, that actually makes inference much more challenging because, again, I have to sum over all the variables. And for a network that's really big, like let's say we have something like this, where here I'm using Q for our query variable, and then we have a whole bunch of variables we don't care about, and then we have some evidence over here. In order to figure out the probability of the query, in principle, we have to sum over all the possible values of all of those intermediate variables. This is also hard in Markov random fields, because recall that in a Markov random field, just to calculate the value of a given joint probability, that's given by 1 over z times some product over our different potentials. And recall that to figure out what 1 over z is, or to figure out what z is, we need to do a sum over all of our variables. So in general, when someone hands you a Markov random field, you would love it if they handed you the z value, the partition function, but in general they don't, because it's so computationally expensive to calculate. So for Markov random fields specifically, we're going to assume we haven't calculated that 1 over z value. Now that's not necessarily an issue. It doesn't necessarily make things any harder than they would be otherwise, because notice when we apply Bayes' rule, the 1 over z occurs both in the top and bottom of the expression. So generally, we can just ignore it in our calculations and just figure out the numerator and denominator and then divide them without having to explicitly factor in the partition function. But in order to get this denominator, we still have to do this big sum over all the variables in the network except for the ones that we've explicitly defined according to our query and our evidence. So it's kind of two sides of the same coin. In all these cases, the big issue is that in general, there are usually a bunch of variables that we don't care about, and we have to marginalize over them, which involves a big, big sum. By the way, in networks where you have evidence for almost all the variables, that is, in general, computationally easy. So the place where we need to worry about algorithmic issues for probabilistic inference are cases where we have unobserved variables. So that occurs very often in machine learning, of course, because there's generally two categories of unobserved variables. There's the labels, things we want to do inference about, and there are parameters. Let's think about the setting where we want to apply probabilistic inference. So in general, it's usually the case that we have a bunch of individual examples here, x1, y1 from 1 all the way up to n. And we have some global parameters that apply to all examples. So we can think of three cases. The first is where all of our data per example is all observed, shaded for observed, unshaded for unobserved. And our parameters are unobserved. So this is the case where that we've been focusing on so far in the course. So a good example of this is logistic regression. We have a training set where we have observed features, that would be our xn, and observed labels in our training set. And the only thing we're trying to learn is the parameters by which the labels are a function of the features. So again, this is what we've been focusing on so far in the course. So we're going to kind of switch gears here and switch to the case that I'm depicting here. This you can think of as the hidden local variables case. That is, we have some shared parameters that determine the distributions for our local hidden variables and local observed variables. But we have some hidden variables for every single example. Note that, and of course we want to do inference over these hidden variables. And now note that these inference problems are in some sense disconnected, right? Because in the language of probabilistic models that we've been talking about, each of these z's are de-separated from one another. Note that there's no path to make them dependent. So we're in particular going to be looking at the case where we have some reasonably complicated network at each example with some number of unobserved variables. So a good example of a case where this appears is a patient diagnosis network that we've said before, where we have, for each patient, we have some unobserved variables, meaning, are they afflicted by various diseases? And then we have a bunch of observed variables, including how they responded to surveys about maybe their family history, about what tests we performed on the patient, and we want to do inference over those unobserved variables. We want to diagnose them of disease. Now, of course, we could also imagine this third setting where we have both unobserved global variables and unobserved local variables. There are a couple of strategies for handling this case. The most common case is to find some training cases where we've observed the hidden variables. That is, we bring it back to this case where we're just trying to do inference over the global variables. Then usually we would do our inference over the global variables. Often, instead of using the posterior distribution over those global variables, we would just use the map estimate and then bring it back to this case where we have just local hidden variables. One reason why it's often okay to just use the map estimate for our global variables is that generally the uncertainty in our global variables is much less than for our local variables. The reason being that in order to do inference over our global variables, we have a huge number of data points, n data points. So often that's enough to give you a very precise estimate for those global variables. As opposed to our local variables, where we might, for example, for a patient, we might have only done 1 or 2 tests. So we should expect to have quite a lot of uncertainty remaining about that patient. So that's option number 1, find some training data where we've observed these hidden variables and bring it back to case number 1. Case number 2 we've already seen, which is to use the EM algorithm. That is, we essentially alternate between doing inference over these 2 cases. So we saw this before, where in the EM algorithm, first we do some inference over our global variables, then we take that distribution we learned, that our Q function, and use it to do inference over our local variables, and then iterate back and forth. So in a way, that kind of splits up our job into the 2 cases. We kind of alternate case number 1 and case number 2. And then option number 3, we're not going to talk about much in this course, is to try to do inference over both at the same time. Of course, option number 3 is the most principled, and if you had kind of infinite compute, that would give you the best answer. However, it tends to be very hard computationally. So we're not going to talk about that in this course, and they tend not to be used in practice. So again, most inference in practice is kind of in one of these 2 settings, either the local hidden variable setting or the global hidden variable setting. And in the case where we have both, we'll usually use EM to kind of split them back up again. So that is to say that the methods we're going to talk about in the next few weeks are going to apply all in this local hidden variable setting. We're going to talk about a bunch of algorithms in the next section. In particular, we're going to take sort of more of an algorithmic focus, less so a mathematical focus, because, as I said, this problem of probabilistic inference is hard computationally. So really doing anything that we could derive mathematically efficiently is a hard problem in its own. We're going to look at 2 categories of algorithms: exact inference algorithms, that is, algorithms that will give you an exact solution to the posterior probability, that is, it'll give you an exact answer to the question of what is the probability of A given B in the probabilistic model you're given. We're going to talk about cases where we're doing exact inference is tractable using these methods. So we're going to give specific cases that we're going to talk about soon, about in which cases we can run these in reasonable time. As we mentioned, doing probabilistic inference in general is NP complete. So we shouldn't be able to do fast exact inference all the time, but turns out we can do it in some settings. Okay, now what if those settings don't apply? Then we will resort to approximate inference. So our exact inference methods we're going to talk about, we're going to start with a method called variable elimination. Then we're going to talk about belief propagation and, in some sense, a generalization of the belief propagation algorithm, which is called the junction tree algorithm. So those are coming up in the next few lectures. Then for approximate inference algorithms, we're going to talk about a method called loopy belief propagation, which is a sort of an approximate version of belief propagation, as well as variational inference, which we'll see if we have time to go into much detail in. I'm hoping to add that since last year. And Markov chain, Monte Carlo, and other sampling-based probabilistic inference methods. So that's what's coming up over the next few weeks.